It's your boy Ape Analytics. How are you? Things are getting serious today because we're talking about Numpy, proper analytics and data science stuff, for real. It's impossible to give you an exhaustive demo of Numpy in a reasonable amount of time. So here's what I'm going to do. Talk really fast and focus on the 50% of things that I use 99% of the time. Every second counts, so let's go. First things first. What is Numpy and why should you use it? Numpy is a package or a library. Think of it as some sort of extension for your Python. Numpy stands for numerical Python, i.e. it is great at crunching numbers because 1. It has a lot of functions for stats such as mean or standard deviation, as well as scientific stuff like square root or cosinus. And 2. It is
freaking fast.
Thanks to the way it stores data in things called arrays. If you want to find out more, here's a link to the Numpy website. Thanks, Ape, but you still haven't told me how to install it. Good news, if you use Anaconda, as I strongly recommended you do, Numpy is already installed. Yay! If you don't use Anaconda, check numpy.org to find out how to install it. But remember, every time you start a new notebook, you need to import the Numpy library. Again, not a lot of work. You just write import numpy as np. The np abbreviation is a widespread convention. But if you want to make your life difficult, you can call it anything you want. So, I mentioned arrays in my intro. Numpy is all about arrays, so let's see what they are and how we can build them. Arrays are kind of like lists, but they are way faster, which is awesome when you are dealing with large datasets. They are not exactly like lists though. You can only have one data type per array, and you can't change the array once created. But that's no biggie, as again, this is the price of tremendous speed. Let's create our first array together. I'm going to call it nada, and I'm going to start with np dot, because I'm using a numpy function, zeros, and I'm going to put a 3, and then I'm going to display nada. This numpy function creates an array of zeros of length 3. Let's check the type of that thing. We're going to use the function type on nada. It is an array. We can also check the data type of the elements of my array using the dtype attribute like so. Name of my array dot dtype. There's no brackets here because it's not a function, it's not a method. It's an attribute of my numpy array. My array is made of floats. You know about the zeros function, so you can probably guess what that function does. Ones. It creates an array of ones. You can also convert a list to a numpy array. So let's consider this list. I'm going to create a new array based on that list using the asArray function. There is a difference between knowing the path and walking the path. Just like you have the range function in normal Python to generate a series of integers, there is the arange function. For instance, we can create an array A using this arange function, and we are going to make it of length 10. And you can select an array's elements like you do with a list. Check out my video on lists if you need a refresher. As you know, a bracket 0 will return the first element of that array. I can also slice using a range. For instance, a brackets 1 colon 3 gives me the second and third elements of my array. And a colon colon minus 1 reverses my array. We can now move on to the shaping and reshaping of arrays. Because yes, arrays have shapes. That's one of their attributes. Let's consider A again. You access the shape attribute like so. We call one-dimensional arrays vectors. But you can have 2D arrays too. And they are sometimes referred to as matrices. And you can reshape an existing array using the reshape method. You simply write the name of your array, .reshape, and give it the shape you want. For instance, here I want a matrix with 2 columns and 5 rows. Likewise, a.reshape25 produces a matrix with 5 columns and 2 rows. If I try to reshape A in a 3x3 matrix, Python doesn't let me, because a 3x3 matrix can't be populated with 10 elements. You can also slice matrices, like you can slice 1D arrays. Let's consider a new matrix B with 12 elements. I want 4 rows and 3 columns. For instance, B brackets 0 colon 2, comma, returns the first 2 rows of my matrix. I can recycle the code above and add after the comma 1 colon 3. And that gives me the first 2 rows and the last 2 columns. Let's consider this new matrix M. You can also transpose a matrix using its T attribute, like this. It's a capital T. Transposing just means swapping rows for columns. So we've seen 1D arrays, vectors, we've seen 2D arrays, matrices. You can even add 1 dimension. Why would you want to do that, you ask? For instance, if you're dealing with pictures, because you need 2 dimensions for the coordinates of each pixel, x and y, but you also need 1 more dimension for the color of each pixel. For instance, a very ugly 4 pixel by 4 pixel image could be encoded this way. I'm going to generate an array of length 48, and I'm going to reshape it using 3, 4, 4, and it looks like this. I have 3 matrices inside, 1 for each color, red, green, and blue. And each element is a pixel. I guess it's hard to picture just looking at numbers, no pun intended, but this is how it works in the background. You can do other things to arrays besides reshaping them, like concatenating them. Let's build 4 matrices of different sizes with zeros and ones. The first one looks like this, just made of zeros. The second one is made of ones like that. The third one is made of zeros. The fourth one is made of ones. I can stitch them together horizontally using the concatenate method. I can do that horizontally using the parameter axis equals 1. Remember this axis thing, we'll get back to it. You see, A and B are now together. And I can also stack arrays vertically using the parameter axis equals 0. So let's do that on C and D. They are now one on top of the other. Easy peasy. But there's many more operations you can do on arrays. You can add them together very easily. For instance, an array of ones of length 3 plus an array of ones of length 3 gives me an array of 2s of length 3. You can even add a constant to an array, and that's something called broadcasting. 5 has been added to each element of my array. If I were to try that with a list, like this, I would get an error. I would have to do, for instance, a for loop. Similarly, you can use broadcasting to divide by a constant. I get an array of 0.25s. You can also multiply 2 arrays together. For instance, you get the product of each element. 0 is 0 times 0, 1 is 1 times 1, 4 is 2 times 2. And you can even compute the sum product of 2 arrays using the @ sign. For instance, we can implement that with one array made of 2s of length 3 and one array made of 4s of length 3. The sum product is 24, i.e. 2 times 4 plus 2 times 4 plus 2 times 4. You can also filter your arrays using true-false conditions. Let's consider this vector x. If I write x strictly greater than 9, I get an array of Boolean values of the same size as x with trues only where the elements verify the condition. I can store this Boolean vector in a variable called mask. I'm calling it mask because that's what it is actually. And I can use that mask to filter my original array like so. Name of my array, brackets, and my mask. It returns a shorter array with the elements of x that are strictly greater than 9. You can actually write the condition straight in the brackets like that. X bracket, x strictly greater than 9, run. Same result. And you can build more complex conditions. For instance, x strictly greater than 9, and using the ampersand, x strictly smaller than 20. I get a vector of 3 elements that verify both conditions. You can also implement the logical OR using the vertical pipe operator. X is equal to 0 or x is greater than 20. You can also use the functions any and all to filter your arrays. Let's consider this 9 by 3 matrix called Y. Using the parameter axis equals 1 to look at the matrix horizontally, I can select the rows that have at least one element strictly lower than 10 using any. I'm going to add my condition, strictly lower than 10, and the parameter axis equal 1, and I get 4 rows. I've returned all the rows from Y where at least one element is strictly smaller than 10. I can use all if I want to return the rows for which all the elements are lower than 10. I only get 3 rows this time, because the fourth row has elements equal or greater than 10. Numpy also has a lot of useful scientific functions. Let's consider our vector x. I can very easily get the mean of x using the mean method, 12. Likewise for the standard deviation, or the max, or even the position of that max using argmax. Let's consider this array of zeros and ones. I can remove the duplicates using the unique function. There's only 2 distinct values. We went from a length of 14 to a length of 2. You have a lot of mathematical functions in Numpy, for instance, square root. The square root of 2 is 1.4. You have pi in Numpy. Another cool function is called linspace. For instance, we can create between 0 and 1 50 points equally spaced and put them in an array. It starts at 0, it ends at 1, and the gap between each element is the same. So let's try it out. I'm going to store in an array called z points between 0 and 3 times pi, and I want 100 points. I'm going to create a vector called sin. That's just going to be the sinus of z, and same with cosinus. And then I'm going to fast forward on the visualization stuff that we're going to touch on in a future video. This is just so I can make a pretty image. Wow, this is pretty. If I were to change that 100 to 10, I get a lot less points. Let's call back our forgotten friend y. We can use the numpy where function on y, which kind of works like the Excel if formula. Here I put my condition, y is strictly greater than 6. Then I'm going to say blue, else I want red. I get a new array of the same size as y, populated with reds and blue, depending on whether the elements are strictly greater than 6 or not. Pretty useful and again, very fast. Let's build this matrix M4 by stacking 3 by 3 matrices of zeros, ones, and twos. The final function that I'd like to show you today is the sum function. Very simply, I can sum all the elements in M4 like that. 27. But like we did for concatenation, we can use the axis parameter to sum row-wise or column-wise. M4.sum axis equals 1 gives me the total of each row. That's why I get 9 elements. And M4.sum axis equals 0 gives me the total of each column, 3 nines. Okay, one last push, we're getting to the end. Randomness. Numpy is great at generating all kinds of random stuff, which is very useful. For instance, many aspects of machine learning require randomness. Which points do I pick to initialize my clustering? Or can I prevent Python from generating new random numbers so that I can reproduce my results? The random module of Numpy holds all that random stuff. And you can import it specifically like so. From Numpy, import random as RD, for instance. And you can then use that RD module like that. Of course, this is exactly the same as writing numpy.random.random10. That random function, by the way, generates floats between 0 and 1. I can also use that rand function, 10, 3 for instance, to generate a 10 by 3 matrix with values between 0 and 1, random values of course. I can also generate random integers using randint. For instance, if I want to simulate a roll of 3 dice, I can do 1 because that's the lowest value of the dice, 7 as the upper bound, that's exclusive, so it can only go up to 6, and 3 for my number of dice. Again, 1, 5, 4, but I can roll it again. 1, 6, 1, 4, 5, 6. You get the idea. So, that was dense. I shared with you my take on Numpy, so now you need to try it for yourself. A nice place to do that is 100 Numpy exercises. You have the link there, and I'm going to add it in the video description as well. It will take you to GitHub. You can download the Jupyter notebook there. You have 100 questions with solutions and hints. It starts very easy, but it quickly ramps up. You've probably had enough of me for the day. As always, thanks for watching. Like, share, subscribe, hit the notification bell, comment to let me know what you think I would like to see next. And remember, practice makes perfect.